Hi. We were examining sequential circuits. We have already examined SSI elements, sequential circuits. This is MSI elements, sequential circuits you see here. MSI element, that's right, yeah, MSI elements here. So there are two groups of MSI elements, sequential MSI elements. One of them is the registers. In Turkish we call them yazmaçlar, and the counters. Registers are used to store the input and output data. So in a digital system, we always need to store the information that we need. That storage could be the data that we are going to put in a system. We've got to store it. We are not going to, in the first stage, we're going to put the data in manually. But after manually we put the data in, we've got to keep that data, we've got to store or keep the data in registers or store in registers. So a digital system does a process. After the process, a new data comes out of the circuit, isn't it? That data should also be stored somewhere in order to examine later on. So where we are going to store this data is registers. So we're going to see these registers. There are different type of registers: parallel load registers, uh, shift registers. These are two main functions related with the registers. If these two functions, put them together in one register, it is called universal registers. So at the end, as you see here, we are going to see the usage of these registers. That's the first group. The counters, there are two groups of counters: asynchronous counters and synchronous counters. We are going to examine separately and then see the applications of these counters. So let's escape from here. Put it down. Anyway, so I've got to the transfer business now. Open board, I've got to come back. Open board and set this to open board. Open board, open board. I got it. Okay. Now that is the parallel loading register. Parallel loading register. So how many inputs, how many outputs? Let me draw these. This is an integrated circuit, MSI element, and it has got many inputs and outputs. So you could see them all here. So these are the outputs. So we've got the total number of outputs. These are okay. Outputs, outputs, 4 of them. And these are the inputs. Let me change it different color. So these are the inputs, 4 of them. Inputs. Another input is that clock is input. So total 5 inputs and 4 outputs. How it works is easy, isn't it? When you this I0, I1, I2, I3 inputs comes directly to the input of D flip-flop. The definition of D flip-flop, as we know, next state is the same as input. So when the clock pulse comes, that data is going to come to the output of this, and the A0 is going to be seen here when the clock pulse comes. and for the second D flip-flop input, I1 is going to come out of here, I1, I2, I3. So what we have done here, in one clock pulse, we transfer these 4-bit data inside the register. So that means we are storing it here. How long we are going to keep it there? Until the next clock pulse comes. Because when this clock pulse, this is raising edge clock pulse, isn't it? When this clock pulse comes, that information is transferred to here. Keep it there until the next clock pulse comes, isn't it? So this time difference here, raising edge, this time interval here is the storage time of this 4-bit data in our register. So that's why it is called parallel load. Why we call it parallel load? 4 bits, that I0, I1, I2, I3, 4 bits, put in one clock pulse, isn't it? So that means parallel loading we have done. The second type of, let's continue on that. In the previous one, we didn't have the load input. Now we've got a load input. We've got these 4 inputs, yes. These were, they were available in the previous one. That clock is also exists in the previous one. But that load is new one. That's the new input. Why do we need a new input here? Because when you do the loading and when you're not do any load, if you transfer that function to a clock, you are in trouble, because clock is the central clock everywhere in your system. So if you are dealing with one register only, you've got to do control of this register by different inputs, not the clock inputs. So this load tells you when we are going to do the loading, when we are not going to do any loading at all. So how it does it, so let's examine it now. If the load is 0, let me write it, that green one, that load is 0, the output of this one is 1, isn't it? And so A0 comes here, A0. So this is a multiplication, 1A0 gives you A0 here. So if this is 0, that is 1. That is the opposite of 1, so that's going to be 0. Whatever the other input here, that's going to be 0. So A0, 0 gives you A0. So when load is 0, your D flip-flop input is A0. Similarly, second D flip-flop input is going to be A1, that's going to be A2, and that is going to be A3. Fourth D flip-flop input. When the clock pulse comes, you're going to transfer this data to here, so no change, isn't it? That means no loading. Now when this load input is 1, what happens? So when this is 1, so the output of this is going to be 0. So this OR gate first input value is going to be 0. So when this is 1, that's going to be 0, and the prime of it, that's going to be 1. So 1, and this is I0. Output of this AND gate is going to be I0, and output of these OR gates, 0 plus I0 gives you I0. So first D flip-flop input, when the load input is 1, is going to be I0. Similarly, the other D flip-flops inputs are going to be I1, I2, I3. When the clock pulse comes after the load equal to 1, if the clock pulse comes in, then at the output I'm going to see A0, A1, A2, A3. After the clock pulse, the inputs transfer to the output, because D flip-flop output next state function is the same as D function. So what we have done is loading. So what is the function of that loading? Is to control the loading function, isn't it? Anytime you like, by this input, that load input, you could do the parallel loading operation, or you don't do it. So that is the control input. We have seen similar control inputs or SSI, SSI combinational circuit or MSI combinational circuit. For example, MUX's decoders, we had enable input apart from the clock input. And in MUX we had control inputs. So that means mode selection inputs. These are all the additional control inputs that we use in MSI elements in combination circuits. Similarly, in sequential MSI elements, we've got control inputs like the one that we see here as load input. So we examine this now. Okay, we examine this. So up to now we have seen the loading operation done by the registers. Now the shifting operation I would like to show to you here. This is a shift register. What is the inputs of this shift register? Let me draw the box first. So that is our box. Oh, you can put that in like that. Goes up to here. And this, let me take this out. So that's going to be now. That's the input. The different color. That is here. Oh, okay. That input, serial input. Clock is input. And that is the output. Output, let me show it different color. This is serial out. That's the output. You might take this A1s, these A's are these all A's as the output as well. You might consider this all output. So what's happening here is this, you see. The data in here is in serial, so this is not at the same time. You don't see all these bits. You're going to see this bit first. In order to do any operation on this bit, you need a clock because these D flip-flops works with clocks. So let's say this A bit related clock is this, A1 bit this one, A2 bit is this clock, and A3 is related to this clocks, right? So let's draw now A0. I've got to, for each clock I'm going to use different colors, so I'm going to clear this. So for this one, so our input for this D flip-flop is I0. When the first clock pulse comes in and the positive edge, because there is no circle here, that information is going to be transferred here. So for the first clock pulse, what about the output of this one? Since the input, this is A3, isn't it? A3 is the input of the second D flip-flop. When the first clock pulse comes, A3 is going to come here. And A2 for the third D flip-flop works when this first clock pulse comes, that A2 information is transferred to the output. For this one, A1 is going to transfer to here. Okay, so for the second signal, use it green. So let's apply the second serial input I1. So for the I1, I'm going to use this second clock here and this positive edge. At that edge, that I1 is going to be transferred to here, I1 here. So before that clock pulse, second clock pulse comes into the second D flip-flop, D flip-flop input is I0. When this clock pulse comes, that I0 is going to come in, I0 to here. So that is I3 is going to transfer here, and I2 is going to be transferred. I0, I3, that's going to be I3, and that's going to be I2. So this is green one. And let me use the red color for the third input. For the third input, I'm going to apply this clock. When this clock comes in, that's going to be I2. That I1 is going to be transferred here. I0 is going to be transferred here. And I3 is going to be transferred here. When the fourth comes in, that means I3. For the fourth bit I3, I'm going to use that clock pulse, fourth clock pulse rising edge. On that edge, that I3 is going to come in, I2 is going to come to this, I1 to this, and I0 to this. What happened here is this serial data shifted in by 4 clock pulses. 4 clock pulses, that means in here at this output here, you're going to see I3, I2, I1, I0. So one of the interpretation that we could say for this shift register, you could say that 4-bit serial data transferred to parallel data, isn't it? Parallel data, that's that data. So another word is this. On this wire, you cannot see all these 4 bits at the same time because they are coming one after another. But after the fourth clock pulse, you're going to see these 4 bits at the same time here. That means parallel data. So that is serial to parallel data transfer that we have seen here. You might also consider this shift register as parallel to serial data as well. So you are doing two things, parallel data to serial data. How we have done it, assume that at the beginning, if you had this information in your register at the beginning, before you apply the first clock pulse. So at the output, you were going to see that I0 here. So this output is this output at the same time. So when the clock pulses comes, from this output, you're going to see I0, I1, I2, I3 after fourth clock pulse. So you're going to see these. That means at the beginning, before the clock pulse, you had these 4 parallel data stored in your register. After 4 clock pulses, you take these bits out in serial one by one from the output. So parallel data transferred to serial data. So as I said before, in sequential circuit, input data and output data are stored in shift registers. Registers, let's say. You might use the shift register or parallel loading registers. So let's come to the second one. This table shows whatever I explained here, it is shown here as a table. And universal shift register here, universal shift register does 2 functions together. Parallel loading, shift right, shift left, and no change. So since we do all the functions within the same element, we call it universal register. So universal register has got 4 modes. In order to apply those in order to separate those 4 functions from each other, I need 2 variables, independent variables. These variables are S0, S1, and meaning of those, when this variable values are 0, 0, shift right, 0, 1, parallel loading, 1, 0, shift left, and 1, 1, no change. So let me draw now the input and output for this universal register. There's going to be something like that. Maybe come out here, come here, here, and here. Okay, yeah. Let me do it. Okay. The inputs? Let me draw the inputs in different color. Let's say that's the input. Okay, input S0, S1. So this is the mode inputs, we call them. According to this mode, we could select the mode of our register. That means shift right, shift left, parallel load, and no change. And these are the other inputs, that A0, A1, A2, A3, I3, sorry, not A. So these are the inputs. And this shift right is another input. And shift left is another input. These are serial inputs. This is serial input as well. So the clock, although is not drawn here, is another input for this central clock, isn't it? So that's input as well. So the total number inputs 1, 2, 6, 7, 8, 9. 9 inputs. If you make a truth table for this circuit, so 9 inputs are going to come here. So the number of rows that you're going to use is going to be 2⁹. These are external inputs, of course. Now, how many internal inputs do we have? Here is the internal inputs. These are the state variables. Since we've got 4 memory element means 4 state variables. So that's going to be plus 4 if total number of inputs. So it's become 13. That's going to be plus 4, 13 to the power 13 rows you've got to put in. And then if you are drawing the mathematical model as a truth table for this circuit, it's going to be Y1 up to Y4 and Z1 point like that. How many Z outputs do we have? These are the outputs. Let me change the color. That's the output, that's the output, that's the output, that's the output. You might consider this one as okay, these are the outputs. So 4 outputs, Z1, Z2, Z3, Z4. So 8 functions that you got here. Next 8 functions, the output functions, if you want to represent it. That's quite long. But what we are going to do here, you're going to make it as simpler. We're going to say write a function table rather than the truth table. So how this works, let's examine this. So I will be using different colors for the different operations. For example, shift right, let's consider shift right and use the green color. Shift right, that is the mode. And shift right is the select input of a mux. Let me remind you how mux works. Mux, 4 input, 1 output, and 2 control inputs. So this S0, S1, this control input, S0, S1. If they are 0, 0, let me clear this. If the control input is 0, 0, So this input is transferred to the output 0, 0. Control input 0, 0. Input 0 is transferred to the output. Input 1 is transferred to the output when this control input is 0, 1. So that is going to be in this, whatever input here is transferred to the output. When it is 1, 0, this third input, second input, transferred to the output. And when it is 1, 1, this fourth input is transferred to the output. So it's going to be similar here. So look at this first input. When we select 0, 0, that means you are transferring that information to here. That's serial in. What about the second mux? All these control inputs, mode selection inputs, are going to be repeated for all the muxes that we've got here. So that's going to be 0, 0, isn't it? When we change that, that's going to be 0, 0. When it is 0, 0, that input, look at this input. Now this mux, 0 input is this, isn't it? A0. So this is A0. So at the output, mux, since the mode is 0, 0, it's going to be this one, A0. For this one, this is A1. So that's going to be A1. And that's going to be A2. So here, that is A2, right? So the output of the muxes are the input of my D-type memory elements. So when the clock pulse comes to the D-type memory element, this D input is transferred to the output, since we know that definition relation of D flip-flop is this. Next state is the same as input. So in here I am going to see SI, A0, A1, A2. A2 is input of the D flip-flop, so it comes to the output of my D flip-flop. So what happened here, in one clock pulse, I put in one shift right data, the new data in. If you apply 4 bits, the 4 bits coming to that shift in is going to transfer to the input of our shift register. That is shift right operation after 4 bits. So if you choose the second mode, let me choose the second mode as this one. So second mode is the parallel loading here. So I'm going to examine the second input. So second input of the muxes are this I0, I1, I2, and I3. So when you choose this mode, these are going to be transferred to the output of the muxes I0, I1, I2, I3. So this I 4-bit data is also the input of my D flip-flop. When the clock pulse comes into these D flip-flops, these inputs are going to be transferred to the output. So it's going to be A0, A1, I2, not A, I should have said I actually, I3. So what we have done in this mode, we did the parallel loading, isn't it? These inputs 4-bit data is transferred to the input of inside the register. That means output of the register. So parallel loading we have done. If you examine shift left now, let make it red. Let's make it black, maybe that is better. Let's make it this color. That's quite. Shift left is this mode. If you apply that shift left mode to all these muxes, that means third input we're going to examine. So this is the third input. What are they? You see this third input here, shift left here. So this is shift left. Means if we choose that load, so that's going to be come in shift left to the output of the mux. What we are going to see here, third input, you see the third input comes from that A3 is coming to here. A3. A2 comes to these marks, and A1 comes to this. Come to this one. You can check it now. This comes from this A1 here, isn't it? This is the A1. So let me draw it. So this A1 goes like that and goes like that and comes to here. When the clock pulse comes, so all these A1, A2, A3, and this serial left is going to come in. So that's going to be A3, A2, A1. That's the output of the mux. At the same time, it is the input of the D flip-flop. So when the clock pulse comes, this data is going to come out here. That's going to be A1, A2, A3, and shift left. So in this mount, what happened is this. Whatever the shift left input bit is going to be transferred to the right-hand side first D flip-flop output. So that means you are shifting the data inside this register to the left, and you're going to put in the first data in serial in to the first D flip-flop on the right-hand side. So if you apply 4 clock pulses, so 4-bit shift left information is going to be transferred inside the register and stored there. The last one, if you look at the last one, is the output is applied to the input. So for the last one, make it black. This is no change mode. So here you are. A0 is connected to this 4th input of the mux. Similarly to this A1 to here, and A2 to here, and A3 is going to come here. So that means all these are going to be also the input of the D flip-flop. When the clock pulse comes, no change. So this is no change. So what we have done here is this. We have seen parallel loading for registers, and we have seen also shift right, shift left operations for the registers. So this universal register, combine them together and put it one integrated circuit. So it is called the universal shift register. Instead of drawing a truth table like that, we write a function table saying that, let me write it here, S0, S1, 0, 0, that's the one, shift right. So that is also this is the function table of a universal shift register. You might consider it like that. Let's see now the application of these registers could be serial header input-output data storage. You see here register A and register B are the registers that you keep 4-bit serial data in. So the numbers that you're going to add, let's say you're going to add number 0 with number 4. You're going to do parallel loading to these registers. So when you click on your keyboard 2, that's going to come in. So this is decoder. And this one is going to come into here. So you do the parallel loading to these registers. That means you are storing your numbers to be added, right? So in here, the parallel ladder that we examined in the sequential circuit synthesis includes only this part, isn't it? That was the circuit that we use. So if you look at this circuit, you are applying the inputs by hand manually we applied this in the lab. And there was one output, the Z. You're going to observe this sum of your A and B as S0, S1, S2, S3 on that wire here. That means on the same wire you're going to observe S0, S1, S2, S3. On the same wire means you're not going to see all these bits in an instant. So you cannot see them all together because there's just one wire there. So how are you going to see this summation? That means if you got this circuit only, that means you've got to keep in mind all these bits coming out. So instead of keeping in mind, you've got to keep it in a register. How are you going to keep it in a register? You've got a shift right register here. If you connect a shift right register, the output, when the clock pulse comes, this serial data is going to be stored in as parallel data. So serial here, in the register, it is parallel. Okay. So similarly, when you apply these, if you say that you're going to add 2 and 4, you've got to apply these numbers starting from the least significant bit one by one. So you're going to apply this first. So that means serial out, isn't it? So you're going to apply this, these operations, get the S0, get the carry here, and apply this second. So it goes like that. So you're going to apply this one by one. That means serial out, doesn't it? Or shift right. Shift right for 4 bits application. So you're going to apply this. So for each shift right, you need 1 clock pulse. After 4 clock pulse, you're going to observe this sum here as A plus B. If there is a carry coming out of your sum number, it's going to be seen here, isn't it? The last carry is going to be here. So if you took this one as well, you could see your number, all the bits at the same time. If you don't use these registers, you cannot see them. So that is the advantage. Right. So that is the end of this video then. So we have seen universal registers, how they run, and 2 application of these registers as an example we have seen. Let me finish that video then.